stable. So a is greater than 0, at the same time a is less than 1 also. So that condition is also something that we must mention. And only if a is less than 1, 1 minus a upon 1 plus a will be a value that will be less than 1. Alright, so that this is what we conclude. We have taken a low pass filter. So in this case we did not consider a 0. If I want to place a 0 and obtain low pass filter, then 0 must be placed in the high frequency region, which is negative real axis. So let's see what is the effect of placing 0 in this particular filter. So now I'm going to take another transfer function h to z. There is some constant 1 minus a by 2 into 1 plus z inverse upon 1 minus a z inverse. Once again, this a is greater than 0 and less than 1. So let us immediately find out poles first. For poles, 1 minus a z inverse should be equal to 0, which means z minus a is equal to 0, and that means once again pole is at z equal to a. And to get zeros, this time we will have zeros also because there is numerator polynomial 1 plus z inverse and equal to 0. This will give me z plus 1 equal to 0, and that means z is equal to minus 1. So we conclude two things. 0 is on the negative real axis, and not just that, it is right on the unit circle, because minus 1 will be a point that will fall on the unit circle. So is that allowed? Is that fine? Will it make system unstable? No, because zeros can be anywhere in the z plane. The condition for stability is that poles must be inside the unit circle. So let us make pole 0 plot. Pole will be somewhere here because it is equal to a, and a is between 0 and 1, but 0 will be on minus 1. So this is minus 1 point and this is a. So just by looking at the pole 0, can you figure out what type of filter it is? Pole is on the low frequency region, 0 is on the high frequency region, and that means it has to be a low pass filter. Let's quickly verify whether it's a low pass filter. For that I will need h2 of omega. Now how do we obtain h2 of omega? By replacing z with e raised to j omega. So 1 plus z inverse becomes 1 plus e raised to minus j omega, 1 minus a e raised to minus j omega. You should always evaluate it for few values of omega. Omega equal to 0 and omega equal to pi should be sufficient in this case. If I take omega equal to 0, then h2 of 0 becomes 1 minus a by 2 is a constant, 1 plus e raised to 0 will be 1 divided by 1 minus a, because e raised to 0 is 1 again. 1 plus 1 is 2, will cancel out with this 2, 1 minus a will also cancel out, so the answer becomes 1. And if I now take omega equal to pi, then h2 of pi will be equal to 1 minus a by 2 is a constant, 1 plus e raised to minus j pi is minus 1 divided by 1 minus a. E raised to minus j pi will be minus 1, so that minus 1 and this minus will make it plus 1 plus a. And this time if you observe, you get 1 minus 1 equal to 0. Now, so this verifies that the filter that we have taken is a low pass filter, because at omega equal to pi, which is the maximum frequency, the magnitude is 0, and at omega equal to 0 it is equal to 1. If I draw the magnitude spectrum, this is how it will look like. So this time it will start from 1, no doubt, but you have to see that this time we will go down to 0 completely. We will not, so in magnitude we will go down to 0. It will not remain at a non-zero point like in the previous case. In the previous case, if you see, your magnitude at omega equal to pi was 1 minus a upon 1 plus a, which was less than 1 but was not exactly 0. Ideally, low pass filter should give you 0 response at omega equal to pi, which is happening in this particular second filter. So both first and second functions are low pass filters, but how are they different? There is a 0 present in the second filter, and that 0 is right on the unit circle. It is at z equal to minus 1. So this is called perfect null. This getting 0 in the magnitude response is called perfect null. Alright, so you get perfect null here. So what is the conclusion? The conclusion is that if you want to have a perfect null, that means 0 magnitude in the magnitude response, then you must consider 0 at that particular specific point. So for example, if you want perfect null at omega equal to pi, then you must consider 0 on the unit circle as well as on the negative real axis, because negative real axis corresponds to omega equal to pi. So now for example, let's say I want 0 or the perfect null in the magnitude response at omega equal to pi. In that case, I will have to put 0 at omega equal to pi. Now what is omega equal to pi? It is the imaginary axis. So I'll have to consider 0 point on the positive imaginary axis, but to get a perfect null, 0 must be present on the unit circle. If I take a 0 at this point, it will give me a perfect null at pi by 2. So this property we will use later on in the design of filters like comb filter and notch filter. So we have taken two examples of low pass filter.